I bought a whole bunch of candy bars from Costco the other day, so I've got a lot to go through. Okay, I think we left off in chapter 4, and we're talking about linear regression. And I made up this fake data set, right? I said x is 1, 2, 3, 4, and y is 2, 6, 4, and 8. And I said, how do we know what is a good fitting line? Okay, and so one proposed line was the line y hat is equal to 2 times x. And so we said, you know, if I graph these points, I got these dots like this. And this proposed line, I forgot what color I used for this, you know, would look something like this. Okay? And we say, well, how good is this line? And we came up with this term called the residual, right? And the residual is the difference between the actual value of a data point and what we predicted for that data point, okay? Okay, or we can write E, the residual, this can be thought of as the error, is actual minus predicted. Or symbolically, we can say E is y, the actual value, minus y hat, which is our prediction for y, right? So I think I said y hat is our prediction. And so we said if we're going to use this as our prediction, y hat when x is 1 is going to be 2, 4, 6, and 8. Okay? And then we can look at the error between the actual value and what we predicted. Okay? So when x is 1, the actual value is 2, and according to our prediction line, we would also predict 2, so we have an error of 0. Okay? When x is 2, our actual value turned out to be 6, but we predicted only 4. So in this case, we have an error of 2. Over here, we have an error of negative 2, and over here we have an error of 0. Okay? Just want to make sure all of these numbers that appear here, this is okay with everybody. If there are any questions at this point, now would be a good time to ask. Okay, so we're all good here, okay? And so the way we're going to evaluate how good or how well our model makes predictions is we're going to look at this error column, and we're going to square them and add them up, okay? So we're going to have the total squared error. I think squared would only have one R. Total squared error. And so this will be 0 squared, which is 0, plus 2 squared, plus negative 2 squared, plus 0 squared. Okay? And so we would end up getting a total squared error of 8. So our total error, total squared error, keep wanting to have this double R, squared error for this line is equal to 8, okay? And we might illustrate this graphically by turning these into squares and say, oh, look at this. You know, the total area of these squares would be 8, okay? Because this would be a 2 by 2 square and something like that, okay? So the total area of these squares is 8. Okay, so that's one possible line, okay? Stats 10, lecture 3. So far, so good? Okay, sure. Okay, and then we'll try another candidate line here, okay? So we got X, and we got Y, 1, 2, 3, 4, the same data, 2, 6, 4, 8. Okay, and then so for this line, my line of fit will go something like this or something, okay? And so this this equation is y hat is equal to 1 plus 1.6 x, okay? Y hat is 1 plus 1.6 x. Okay, so in this case, when x is 1, what do I predict y hat to be? 2.6, okay? And then when x is 2, I would predict y hat to be 4.2. And then, you know, I might have to do some math here. 3 times 1.6 is, well, that's not helpful. 5.4, so I have 6.4. Wait, something is adding up funny. Did I mess something up? Oh, I did 1.8. Okay, no wonder. Okay, so 5.8. And I think this is 7.4. Is that me? What is that? It's like a cell phone ringing while... No, not me. Nobody's gonna call me. Okay. So this is y hat. So this is what we're predicting. And then so here our residuals, you know, would be kind of the vertical distance between the line and the thing here. So our errors here would be, you know, again, E is the difference between y and our prediction for y. So here I get negative 0.6. Here I get 1.8 and 1.8 and 0.6. All right, this was negative. Okay. Okay, and then so our total squared error is equal to 0.6 squared plus 1.8 squared plus 1.8 squared plus 0.6 squared. Okay? So let me just kind of change my mode here. Okay, so I got 0.6 squared, which is 0.36, and 1.8 squared is 3.24. So I'm going to add this. So I get a total of 7.2. Again, just want to pause and make sure everyone's okay with how we're arriving at these things. Okay, so here, I just kind of gave us two candidate lines. So if you're asking where I got 1 plus 1.6x, the answer will be, I'll tell you in a minute. But so as far as this line goes, we have a total squared error of 7.2. Okay, so we can draw little boxes to say this is, you know, if we looked at the area of these boxes, the area of these boxes will be 7.2, okay? So in lab 2, you'll kind of explore, I don't know, fitting different regression lines and and seeing how the boxes fit. So that will be lab 2. Okay, I hope everything with lab 1's going okay. Yeah? Well, okay, that's due Friday, right? So, okay, so between these two lines, y hat equal to 2x and y hat equal to 1 plus 1.6x, which line would we say is the better fit? This one, because the total squared error is less, okay? So, you know, because this line has a smaller total squared error, we will say this line is better. Has a lower total squared error. Is a better fit to the data. Okay. And so linear regression is often called least squares regression because we're trying to make the total squared error as small or as least as possible. So far, so good? Okay. Okay, and so I'm going to kind of just skip all of the math that goes into how we decide how did we figure out what our intercept and what our slope is, okay? So basically, you can do calculus, and we're not going to do this, but you can do calculus to find out how to minimize the total squared error. Okay? And when you do that, it turns out you get nice little formulas for the slope and intercept, okay? So the results say that, okay, the best fit line will have the following slope and intercept. Okay, so the slope is b, okay, and this will be r times the standard deviation of y divided by the standard deviation of x. Okay, so r, what is r? This is our correlation coefficient. Okay, S sub y is the standard deviation of the y values. Sx will be the standard deviation of the x values. Okay, so that's slope. And then we have the intercept. And that will be y bar minus b times x bar. Okay, so y bar is the mean of y values, and x bar is the mean of the x values. Okay, and b is the slope, okay, which you've calculated in this step, okay? So to get the slope and intercept, you just need these 5 values, okay? 5 values needed. So if you have these 5 values, you can get your slope and intercept for any data set with whatever you want to call it. two numeric variables, okay? Two numeric variables, you can fit this. Okay. Good? No. Okay, so I'll let you guys write that down. But conceptually, are we good? Yeah. Okay. So this is just the results of calculus showing that this is how we get it. Okay. All right, let me find a good example for our problem that I want to do. Okay, so I'm going to flip over to the next slide, and let me find the picture that I want. Okay, this is the picture. Okay, you can draw a, you know, some version of this thing in your notes if you want. Okay. All right. So what this is we're looking at a bookshelf. Okay. And so imagine we've got some kind of book here. This is my beautiful illustration. What book is this? This is going to be called Stats 10. All right. And what we're going to do is we're going to measure how wide this book is. Okay, so we're going to measure the width. Okay, and then we're also going to look and count the pages. And so we're going to have two variables. X, the number of pages we have will be X, and the width that we find is Y. Okay. And then so we find a bunch of books, and here's a book with like 90 pages, and it's like 6 millimeters thick. So the width is measured in millimeters. Okay. And we go through and we gather a bunch of books. We measure how many pages it has, and we measure its width, and then we fit a regression line. Okay, so this is what we get. Okay, and overall, it looks to be a linear relationship. In general, books with more pages are thick or have great width. Books with very few pages generally have less width, and I think that matches our experience in life. Okay, unless we're talking about like children's board books, and that's like a different thing. I don't think they're included in their analysis here. Okay, and so we get our equation will be width hat is equal to 6.22 plus 0.0366 pages. It's okay? All right, so this will be our clicker question 1. Okay, and I'm going to say the value 0.0366 in the regression equation is okay, so your answer choices are the correlation, the intercept, the slope, or the residual. Okay, so clicker question 1. I hope this works. Okay, everyone's clicking in the thing. Okay. So So we have width hat is equal to 6.22 plus 0.0366 times pages. So does that represent the correlation, the intercept, the slope, or the residual? The value 0.0366. Okay, so we'll say 10 seconds. Get your clicks in. Three, two, one, click, 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 and stop. Okay, so our answer is indeed C, okay? So answer choice C, 0.0366 represents the slope, okay? So we said, so this is the slope. This over here is our intercept. Okay, so we said in statistics we have the form y hat is equal to a plus bx, where b is our slope and a is our intercept. Okay, so 0.0366 is our slope, 6.22 is our intercept. Okay, so based on this, if I plug in a book with 400 pages, how wide do we predict it will be? So let me see if I can copy this. Copy this onto our next slide here. Okay, so I'm going to say if a book has 400 pages, what is its predicted width? Okay. I don't feel like making a clicker question out of this, so we'll just we'll just have you guys do some calculations here and tell me what your answer is. So what do we get? Do we get an answer? 400 times 0.0366. Whoops. I don't know what did I do? Okay. No, I'm sorry. 6.22. Huh? 6.22 plus 0.0366 times 400. Okay, I get 20.86, right? So this is how wide we predict our thing to be, okay? What does the hat represent over the width again? Yeah, so the hat means our prediction. Okay, so width would be actual width. With hat would be predicted width. Okay, so when if x is 400, predicted width 20.86. Okay, what happens if x is 500? What is predicted width? $24.52, okay. And if x is 600, what is our predicted width? $28.18, okay? Is this okay with everybody? No questions here, okay? How much to go from this prediction to this, how much did my prediction change? What did I add? What's that? 3.66? And how much did the prediction change from here to here? 3.66, okay. So if I said 700 pages, what would we do to 28.18? If I could plug in this thing, but I could just also add 3.66, right? Okay, so where am I getting this 3.66? It's coming from the slope, right? So this points to the interpretation of the slope, okay? So here's our generic interpretation of the slope. Which will be, if we increase, the interpretation of the slope is how much we expect y to change, or how much our prediction for y changes. Our prediction of y changes if we increase x by 1. Okay, or if x increases by 1, I should say. Okay, so what this is essentially saying is that if you add 1 page to a book, our prediction for the width of that book goes up by 0.0366 millimeters. Okay, so it's a very small amount. If we add 1 page to a book, we're essentially saying, you know, and actually 1 sheet is 2 pages, so we're saying like you add 1 page and it's going up by, the width of the book goes up just by a tiny bit here, okay? It makes more sense, so in the context of pages, you know, the interpretation of the slope basically says that we predict the width of a book to increase by 3.66 millimeters, okay, if the number of pages goes up by 100. Okay, so if we added 1,000 pages to a textbook or a book, how much do we expect the width to increase? 36.6 millimeters. Yeah? Okay. We're good? Okay, we're good. Okay, so let's talk about the intercept. Okay, and so the intercept is 6.22. Okay, and so so the interpretation of the intercept basically this is our prediction for y if we were to plug in 0 for x. So, you know, one warning is that in some cases, or in many cases, it will not make sense to use 0 for x. Okay, and in that case, in those scenarios, or in those cases, the intercept will not have a practical interpretation. Okay. Okay, so, all right. So what does 6.22 represent? Okay. Can we think of a practical interpretation for 6.22 here? Okay, so I'll maybe, yeah. Okay. I don't want to make too much of these trap questions for you guys. Okay, so whoa, I don't know what just happened there. Okay. All right, so practical interpretation in this case would be the width of a book that has 0 pages, right? So 6.22 would be our predicted width. With 0 pages. All right, so a practical interpretation would be, this would be the thickness of the covers of a book. Okay, so we can think of it as, could be thought of as book covers. So if I were to just tear out all the pages in this textbook, I would be left with just the covers, and if I measured the width of the covers, maybe I would get 6.22 millimeters, something, okay? It's a possible interpretation. And sometimes you find old textbooks or old books that are falling apart, and you just have the covers, right? So. Okay, all of this regression stuff, it's important to keep in mind what our x and what our y variables are. Okay, so which is x and which is y. Okay, so the x variable is the variable used to make a prediction. Okay, so the synonyms or other terms for the x variable include the predictor, the explanatory variable, and the independent variable. Okay, and then the y variable is the variable that we are trying to predict. Okay, and its synonyms include the predicted variable, the response variable, and the dependent variable. All right, so let me just kind of make up a few examples. Okay, so let's say you want to estimate your fuel consumption based on the distance of your next road trip. Okay, so this will be your clicker question. Okay, so what is the explanatory variable? Okay. Okay, so this will be distance in miles, duration of trip, gas, or cost of gas, gallon or gallons of gas used. Okay, so you can go ahead and start clicking your answers here. I guess duration of trip will be measured in hours. Okay, 5 seconds. 3, 2, 1, and stop. Okay. So then, yes, our answer is A. Distance in miles would be our explanatory variable. Okay. Because this is what we are using to make the prediction. Okay, and so our regression equations would be in the form of, okay, so this will be question 2, or the next one, question 3. Would be in the form, okay. Distance is equal to A plus B times time. Gas predictions. Okay, so we'll go ahead and fire that one up. Okay, just a couple more seconds here. All right, I'm going to go ahead and click stop here. And looks like almost all of you guys got it. I don't know who clicked E. Someone did. Wait, where did this... What? Something happened. Hang on. Oh, there we go. Okay. Yes, that is our correct answer for there. So it'd be we are trying to predict gas mileage. Okay, so predict gas mileage predict gas usage based on distance or mileage traveled, right? Okay. Okay, so we'll end here today. So next Friday, so 1 week from Friday, we will have a midterm exam. The midterm will cover just chapters 1 through 4. Okay, so I'm gonna wrap up chapter 4 tomorrow, or not tomorrow, on Friday. And then the next Friday's exam will cover chapters 1 through 4. And then I will start chapter 5 next week, but that will not be on the midterm. Okay.